Hello and Assalamualaikum. My name is Muhammad Syami Azan bin Syafiq Effendi. My matrix number is DE220191. We're from Group 4, Section 1, and this is the presentation of Experiment 2 of BEV40702. So to start is the first one is task 1. Task 1 is the analysis of electric field between electrodes. So first thing is the introduction. So the application of the finite element method or FEM has been a breakthrough in the magnetic system analysis and design process. The new numerical method is very powerful tool that allows researchers and engineers to model, simulate, and analyze with unprecedented computer accuracy and efficiency. In the scope of this design project, the general aim is to investigate and open the potential of FEM as a tool for achieving technological innovative and pushing the limits to the magnetic device. So the next one is the scope project. Task 1 focus on the analyzing the electrical field between the two spherical electrodes, one connected to the high voltage source and the other one is grounded. We'll be using the FEMM 4.2 software to simulate the electric field for various gap distance. Then we'll calculate the maximum electric field or Emax, compare it with the theoretical values and for efficiently evaluate how efficiently the electric field is distributed between the spheres. So the objective of the task first one is to model the electrical field between the two spheres using the FEMM software. The second one is to simulate and record how the electric field charges with different gap distances. The third one is to calculate the maximum field strength and compare it with the theoretical values to see how accurate the simulation are. And the fourth one is analyze the electrical field utilization factor to understand how uniform the field is. And the last one is explore why understanding the maximum electric field is important, especially in a high voltage application. Now for the methodology of the task 1. So this is the flowchart of the methodology. So first is start and the second is research the analysis of electrical field between the two design electrodes. Next one was to the model using the FEMM software. This is the model of the two electrodes design. And the third one is the choose properties and set parameter on the model. Properties like air, high voltage, ground. And the next one is run simulation from the parameter. So and the next one is the set parameter with a different value and run simulation. This is after the run simulation for the parameter for the first one. And the last one is result analysis and submission. That is the end of the flowchart.
Hello, Assalamualaikum. My name is Muhammad Azmi, and today I will explain to you how to do an analysis of electric field between electrode using FEM. The gap we use here is 2 cm, and the radius of both electrode is 25. So we need to set the knot first. Here is 2 and set 1 and -1. Oh, my bad. Set knot first. 0, 1, -1, 51, 0, 100. Connect clear node. To the curve. The edge angle is 180. Okay. Then we set the here in properties we need to set the material. Material here is air 11 or HE, and boundaries, the open boundaries we use here to place is 1.18. Then we need to set the two properties, and the voltage we use here is 313 kilowatt, and the ground we need to set 0. Then here select this and set the type of torque is air, and this curve is open boundary. Both of this electrode you need to set it high voltage and ground, and we simulate it. After we simulate, we can monitor the heat of this. Okay, so this is the voltage plot. This is the magnetic field. Then if we need to find a graph, let's set this point and this point, set a graph, and what we want to see first. For example, the voltage graph. This is a voltage graph for this simulation, and we can do the magnetic field intensity also. So this is a graph for 2 cm gap between electrode. So that's it for me. Thank you.
So I want to summarize the result from the simulation. So as we know, we take like at least 13 gap distance, 13 type of the gap distance. First one is 1, and then 1.5, 2, 2.5, 3, 3.5, 4, 5, 7.5, 10, 12.5, 15, and 17.5. We use the same voltage, that is 314,000 kilovolt. So because of the gap distance and the voltage difference, the maximum electric field is like in the table. That is the result for the simulation. So now I'm going to talk about the plot graph or the manually plot graph between the voltage against gap distance. So as we can see, the voltage is just the same because we choose 314,000 kilovolt, and the gap distance is between what we choose from before. So as we can see from the graph of maximum electrical field against gap distance, we can see that the graph is gradually going downwards. This is because the electric field maximum is inversely related to the gap distance between the electrodes when the constant voltage is applied. That constant voltage is, as we know, is 314,000 volt. Uh, Specifically for this, as the gap distance widens, the electric field lines spread out, reducing the field intensity between the electrodes. That is why from the graph we can see that the electrical field is going downwards while the gap distance is increased.
Discussion of field uniformity. Due to their curve shape, spherical electrode create a non-uniform electric field, especially near the electrode surface where the field line is curved. The simultaneous result confirms that the gap between the electrode increase and the field spread out and become more uniform. This trend is shown by the field utilized factor, which decrease with a wide gap, indicating a more even field distribution. At the large gap, Emax is lower in simulation due to dispersion. At a smaller gap, Emax is slightly higher to the field crowning. For the conclusion, that the numerical tools are essential for designing safe and reliable high voltage system where the field uniformity is the key. For the conclusion, the simulation of electric field distribution between electrodes using FEM software clearly show that the field is non-uniform, especially near the electrode surface. As the gap between electrodes decrease, the peak electric field max is increased, while the simulation result mostly match the theoretical value. Small difference appear to the complex factors like phasing and boundary effect of theory can fully capture. The field utilization factor also follow expected trend. Large gap lead to better field uniformity and lower field intensity. Thus, SI highlight the importance of the accurately.
Now I'm going to talk about the task 2. So the task 2 is about analysis of force of gap CI core. So for the introduction, magnetic field and forces are highly significant in everyday life, as many devices rely on the magnetic principles. Lifting electromagnets, specifically designed with the magnetic circuit, is commonly modeled using the prototype of CI core structure to simulate the magnetic lifter. This design simplifies the concept while offering the practical representation of how such equipment or component functions in the real world applications. It allows users and researchers to visualize and understand the operational mechanics of electromagnets used in the industrial lifting task effectively. So next one is the scope project for the task 2. For the scope project is the analyzing the vertical and horizontal forces acting on the gap CI core structure, and the goal is the goal of the task 2. The I core feels the pull of the magnetic field, where the C core is composed of the magnetic material. These forces, strength, and direction must be precisely measured and recorded. The values of the flux density, magnetic field strength, and current density should also be certain. So the next one is the objectives of task 2. The first objective is to gain solid understanding of electric fields in electrostatic scenarios and magnetic fields in electromagnetic problems through finite element analysis. The second one is to develop a finite element model by taking into account material properties, appropriate boundaries conditions, and mesh generation techniques. And the third one is to explore the behavior of the system with open boundaries conditions in unbounded domains. And the last objective is to grasp key concepts such as leakage flux, mature flux, fringing effects, and the electromagnetic forces within the electromagnetic system.
Assalamualaikum. My name is Muhammad Faiz Farhan Razam and my metric number is DE22084. So now I want to explain about the flow chart of meteorology. First start, and then after the start we select magnetic problem and then go to the define problem definition. After define problem definition, build geometry using FEMM and then adjust material. So for the adjust material, we have all parameter achieved and we check parameter. If all parameter achieved is no, we go to the recheck parameter and then adjust material back. For if all parameter achieved yes, we go to the next save and run the simulation and then do all boundaries achieve. So for the do all boundaries achieve, we have if no, check and update the boundaries and then go back to the save and run the simulation. If yes, go to the process the result and then stop. So go to the next part. Okay, next I want to explain about the flow of simulation procedure. So this is a FEMM software. So next, after we get this result, click the merge yellow button. Then after click the merge yellow button, we can generate the merge. Okay, after generate the merge, click the glass button. After click the glass button, we will go to the next part. Okay, for the next part is we need to zoom in the model, and then zoom in the model and click the color button on the toolbar. And then a new dialog box appears and we check the option show density plot. This enable a color visualization of magnetic flux distribution, helping us better understand the simulation result. And then we choose the flux density. We have flux density, field intensity, and current density. So first we choose the flux density. Okay, and then click OK. That we can get the result. So for the flux density, click right here. And then with a peak of flux density is 21.8 21.48495 Tesla. And then back. Now we change the plot value. Okay, go to the field intensity. Okay, for the field intensity, we click right here. Okay, so we get the answer is H. We can get the answer H 1.03484 exponential plus 006 ampere per meter. So click right here or here. This is for field intensity. Okay, next we will change the current density. Okay, for the current density, okay, we can get the result. So this purple color, click the purple color, and then we can get the result. For the current density, okay, current density is for 1.6667 mega ampere per meter squared. Okay, so next is select ICO block to analyze the force exerted by the electromagnet on the ICO. We click the block selected. Click the block selected button and highlight the ICO region. This selection prepare the model for the next step in calculation of magnetic force. And then click the integrate. After you click the integrate, choose the force via with the stress tension. Okay. Click and then click the OK. Then we can get the X component is negative 145.0x7n and Y component is negative 0.0159492n. Okay, alright. That's all for me. Thank you. Next, about the discussion for flux density. Flux density noted as B indicates the concentration of magnetic flux within the core material. From the simulation, the highest value recorded was 2.48971 Tesla, especially around the coil area. This showed that the CI core design efficiently channels magnetic energy, reducing losses and avoiding saturation. A high flux density in the correct area confirms the sustainability of the core material and geometry. Okay, next about the discussion field intensity ampere per meter. Okay, first, field intensity represented as H and measured in amperes per meter. Describe the strength of the magnetic field inside the core. From the simulation, the peak value was 1.03511 10 to the power of 6 ampere per meter with 3 major high intensity zones. The region show where the magnetic field is most concentrated, helping designers evaluate core performance under different loads and avoid magnetic saturation. Okay, next discussion current density. Okay, for the current density denoted as J shows how electric current is distributed across the coil's cross section. The simulation recorded a maximum of 41.6667 mega ampere per meter square with the highest concentration near the coil shown in purple on the map. This helps us understand where electric activity and heat are highest so that we can design the system with better thermal performance and durability. Managing current density is key to improving system efficiency and reliability. In conclusion, this project successfully demonstrated the magnetic behavior of a gap CI core system using the FEMM software. We analyzed key electromagnetic parameters such as a flux density, field intensity, and the magnetic force distribution within the system. The simulation revealed that the strongest magnetic field was concentrated at the air gap due to its low permeability. This matches theoretical predictions. FEM also enabled accurate calculation of the magnitude and direction of the force acting on the I core, which is crucial for magnetic lifting applications. Additionally, we validated the core's magnetic properties by calculating the relative permeability using the average flux density and now excitation current. Overall, FEMM has proven to be a powerful tool for simulating, designing, and optimizing electromagnetic devices. So this study clearly highlights how core geometry and air gaps play a major role in force generation, and insight valuable in industry magnet design. That's all from us. Thank you.